Welcome to another podcast. This episode we're going to be taking a look at our first sort of numeric example involving the eigenvalue method. These next four videos you're going to really want to concentrate on because a lot of the rest of the semester depends on you being able to do this process quickly and efficiently. And I want to start off just by giving us a matrix here. So we're just going to look at the matrix A, and I'm going to give us some values here. And so I want to solve this system of differential equations. And I know you're saying, but it's not a system, it's a matrix. Well, if you watched the previous video where I explained the eigenvalue method, one of the things we talked about in there was all you need to know is the matrix. The matrix describes everything, it holds all of the information. So if you're more comfortable knowing what the system is, then the system is, suppose we have x and y. We're going to take the derivative of each of those, subject to this. So this is the matrix form of this system. So here's the system I'm looking at, or maybe once again you're more comfortable looking at it like this. So x prime of t equals 9x plus 5y, and y prime of t equals negative 6x and 2y. So regardless of how you're comfortable looking at the systems, whether in matrix form or system form, it all comes back to what the coefficient matrix actually is. So if this is my coefficient matrix, it completely describes the system, and what we're going to undertake now is the eigenvalue method for solving that system. So here the system would be, or the way that I would handle this is I need to know what my characteristic polynomial is. Remember, it's the determinant of a minus lambda I. It's lambda squared minus the trace. So it's the trace of a plus the determinant of a. So this is lambda squared minus the trace of the matrix is 9 plus 2 is 11. Sorry, it is not. That is incorrect. That's incorrect because I wanted this to be a negative 2. So my apologies. This should be a negative 2 there. Alright. So this is minus the trace of a, and the trace of a is 9 minus 2. And the determinant of a is going to be 12 here. You're going to take 9 times negative 2 is negative 18. Negative 18 plus 30. So that's 12. So this is lambda squared minus 7 lambda plus 12 equal to 0. This factors into lambda minus 4, lambda minus 3. So no matter how hard we try, we can't get away from this characteristic equation. So here are my eigenvalues. Once we have the eigenvalues, we're going to break it up into cases. So we'll start with case 1 is suppose that the eigenvalue is 4. Then what I'm looking for is a solution, which I'll call x1, equal to a eigenvector alpha 1 times e to the 4t. So that's the solution that we're hunting for, and we're trying to find the value of alpha 1 that makes it a solution. The value of alpha 1 is the corresponding eigenvector for lambda equal to 4. And so I'm looking now at the matrix A minus 4i, which means that I'm going to subtract I'm going to subtract 4 from the diagonal. So if I take the matrix A and subtract 4 from the diagonal, 9 minus 4 is 5. Negative 2 minus 4 is negative 6. And here's the way to check yourself. The matrix that you end up with here should be redundant, meaning it should be singular. You should have the columns should be linearly dependent, which these are. You can see that they're in fact the exact same column. That means we know we've done a good job. So I'm going to replace the vector alpha now, alpha 1, with components a1 and a2. And we're going to set it equal to 0, 0, and we're going to solve for a1 and a2 that makes this work. Well, here it's very, very easy. You can see that I should just have a1 to be 1, and then a2 would be negative 1. So, or I could reverse those. Remember, this is only unique up to multiplication by a constant. So what I get from this is alpha 1 is the vector 1, negative 1. So we have our first eigenvector. And then we're going to find our second eigenvector by looking at the case for lambda 2. So suppose instead now the eigenvalue is 3. Then this will give me a second solution. And the second solution corresponds to a different eigenvector, and then it would be e to the 3t, would be the exponential there. And so looking at this, what we would have is we'd be looking at a minus 3i times this alpha 2. And so that would be, I'm subtracting 3 from the diagonals. So I get 6, 5, negative 6, negative 5. Notice once again that they are constant multiples of each other. So we know we've done something correct here. It's a little bit harder to figure out what the values of A1 and A2 should be for this, but let me show you a trick. We would like to have constant values. So the easiest thing to do is always just to let A1 be 1. Okay? So if A1 is 1, what does A2 have to be? Well, A2, so the thing that relates them here is, so for this first line is 6A1 plus 5A2 needs to be 0. Well, if I let A1 be 1, then this is 6 plus 5A2 is 0, or A2 is negative 6/5. But that's not really nice to look at. Remember, I can take any constant multiple of these. And so what if I multiplied both of these by 5? So if I multiplied A1 by 5, it would be, okay, let's try A1 equal to 5 instead. And then multiplying A2 by 5, I would get A2 as negative 6. And that still works. Because if you take 6 times 5, it's 30. And then if you take 5 times negative 6, it's negative 30. Add them together and gives you 0. The same thing is true for this row as well. Negative 6 times 5 is negative 30. And then here you're getting plus 30. So that's the group that I want to go with, and that gives me an alpha 2 now. That's equal to 5, negative 6. Remember that this is, once again, it's unique only up to multiplication by a constant. And so putting this all together, this suggests that my solution is the vector x, which has components x and y. And those components are equal to c1 x1 plus c2 x2, which is c1, here we have alpha 1 is 1, negative 1 times e to the 4t, plus c2, alpha 2 is 5, negative 6, e to the 3t. And so this is my x1, and this is my x2, and together they form a fundamental set of solutions. So maybe I'll just back up for a second. So x2 here is 5, negative 6, e to the 3t. That's one part of my fundamental set. And then the other part of my fundamental set is over here. I get 1, negative 1 is my eigenvector there, and it's e to the 4t. So that's the x1. That's the other part of my fundamental set. So those form my fundamental set of solutions, and then you know it's just a constant multiple of the fundamental set. So x1 and x2 are a fundamental set of solutions, which means that x1 and x2 are linearly independent. You could use the Wronskian on each of those to figure it out. Now, if I wanted to give the solution back in terms of this view, so if this is the view you're comfortable with, then the way to do this is by pointing out what the top component and the bottom component are separately. So what I mean by this is, what is x of t? Well, the function x of t is the top component of the vector. So the top component of the vector would be c1 times 1 e to the 4t. So it would be c1 e to the 4t, and then the top component of this vector is c2 5 e to the 3t. So it would be plus 5 c2 e to the 3t. And then y of t would be the bottom component of the solution vector, which would be c1 negative 1 e to the 4t, so negative c1 e to the 4t. And then the bottom component of this vector would be negative 6 c2 e to the 3t. And so there's lots of different ways to think about the solution here. You can think about it in any of these different forms. So all of these are reasonable. But the solution is basically found by taking the eigenvalues and eigenvectors. So each of these is a solution. All right, thank you for watching.